Hello, welcome back to another video. Today we're going to be talking about the derivatives of exponential functions. So originally I was going to combine this with the logs as well, but I didn't want the video to be too long, so I just decided to separate them into two different videos. This is going to sometimes incorporate the chain rule as well, so I'll review you on that if you haven't watched it, but I do implore you, if you haven't, to watch the chain rule video just so that you know what the chain rule is and you can just kind of easily apply it to these exponential ones. But what you really want to understand is that when you're having the derivative of e, if you remember, e's derivative is just itself, but that's only if it's e to the x. If anything is different about the x, it's not just going to be e to the x. So the rule for the e's is going to be as follows. So we know the derivative of basically, let's just say e to some value u, is going to be just e to the u. So essentially we just rewrite the e to the u again, and we're going to multiply it by the x or the u here, its derivative. So if this looks like the chain rule, it's because it is the chain rule. It's just we have to remember it, especially for the e's, because it uses it all of the time. But the reason why it's the e is interesting is because you have to differentiate it from the actual just general exponent problem. So if there's any other base besides e, it's not going to be as similar. So if we had some value like a, so some other base to u, that's just going to be equal to a to the u. So far it's the same thing. But the difference is we have to take the ln, so the natural log of the base. So a, whatever the a is, we take the log of it, and we multiply by the same thing again, so u prime. Okay, and that's going to be how the exponential derivatives work for exponentials. Just remember, the reason why we don't have an ln for the e, we technically do, but if you remember, for the general for exponents is ln of the base. Well, if we do ln of the base, which is e, well, ln and e cancel and just create 1. So because multiplying by 1 doesn't do anything to the function, technically we are multiplying with the ln of e. It's just, it doesn't really change anything, so we usually exclude it. But we're going to try a few problems, and you'll see it's not too bad to do them. So let's just say the first problem, we had something like this. What if we had f of x equals to, let's just say, e to the x squared minus 4x. So we can't just rewrite it as e to the x, we have to use this formula. So what would it be? Well, the first part, we'll just rewrite the same thing as it exists. So e to the x squared minus 4x. Then we just multiply it by the derivative of whatever it is. So this is the inside one, or the whatever it's raised to. So this part right here. So this is u. So we put the 2 down and we decrease it by 1. That would be x squared's derivative. And then 4x we know would be 4 because x is 1. So minus 4. And that's usually how you would put it. But if you want to make it a little clearer, you can get rid of the multiplication sign and just say this is e to the x squared minus 4x multiplied by 2x minus 4. And this would be the answer, just like this. So not too bad to use the rule. So just like the chain rule, it's just kind of requires its own thing because we do have to remember the ln's for non-e functions. So let's try a similar function and see if we can do it that way. So what if we had something that looked a little odd, but it doesn't really matter. So what if we had sine of x plus cosine of x, so e to the sine x plus cosine of x. What would we do here? Well, the same thing. We would just go ahead and we would rewrite the first part, so just rewriting it again, sine of x plus the cosine of x, and we would multiply it by the derivative of u. So sine's derivative is cosine of x, and cosine's derivative is negative sine of x, so negative sine of x. So even if it looks kind of weird, the process is still the exact same. Let's try another one, so with e's, since we're kind of on a roll with those e's, right? So what if we had e, but kind of a weird one? What if it was root x? So we don't have x, so we can't just rewrite this as e to the x for the derivative. So what would we do? Well, if you don't know the derivative for root x, that's okay. You can still do it the same way. So let's, again, just rewrite the function, and we're going to multiply it by the derivative of root x. So if you don't know, it is going to turn out to 1 over 2 root x. That's just what the derivative of root x is. But if you don't know, like I said, just turn this into the x to the 1/2. You put the 1/2 down, then you decrease by 1/2, or I'm sorry, by 1, so by 2 over 2. Then you get negative 1/2. And then you can just put that into this form. So put it to the bottom, then the halves goes 1 over 2. So it's the same thing. If you don't memorize root x, you can always just find it using the power rule. But regardless, this is the answer. It's going to be the root x multiplied by 1 over 2 root x. So as you can see, the process is pretty similar to the chain rule. It's just we're going to be incorporating differing things. So let's just say we had something involving not an e base, so we have to actually use the second formula instead. So what if we had 3 to x squared to the minus 2x, something like that. So we don't have the exact same thing, but we should be able to find it in a very similar way. So I apologize, it should be f of x equals to. So f prime of x, again, very similar formula. We start off with just the a to the u, so we're going to rewrite the function as it is. So it's just going to be the 3 to the x squared minus the 2x. Then we just take the ln of the base. So the base in this case is 3, so we're going to multiply by the ln of 3, so just the ln of 3, and then we're going to then multiply by the derivative of the inside. So x squared, we already know, is 2x, and then negative 2x would be negative 2, and that would be your answer. So it's just kind of memorizing the formula, spitting out the 3 parts of it, and this is the answer. Sometimes teachers like you to put the ln in the end or in the middle, just ask them what they want, but it's the same exact function. Okay, let's try something similar then. What if we had something like, let's just say, 2 to the maybe x cubed plus 4x plus 2. What would we do here? Well, we should be able to do the same exact thing. f of x. Okay, so the f prime of x would be, again, just rewriting the function as it's presented here for you. So 2 to the x cubed plus the 4x plus the 2. We're going to multiply by the ln of the base, so ln of 2, and then we're going to multiply by the derivative of u, so the exponent. So that's both 3x squared, bring the 3 down, decrease by 2, or decrease by 1, and then 4, x is just 4, and this would be your answer. So even if they give you some insane thing at the top, if you follow the formula, you're not going to be in harm's way. It's going to be perfectly fine. Okay, let's try something else, but I wanted to essentially give you just something kind of similar but using the base. So what if we had 4, but what if we had like something x squared plus the tangent of x? Could we do it as well in this case as well? Yeah, we could do the same exact thing. So all we would do is we would rewrite the first part, so 4 to the x squared plus the tangent of x. Then we multiply by the bases, so the ln of a, so the ln of 4 in this case, so the ln of 4, and then the derivative of the u, so the exponent. Well, x squared is 2x, we know that. And tangent of x, that derivative turns out to be secant squared of x. So secant squared of x, and that's your derivative. So as you can see, it doesn't matter what kind of weird top exponent they give you. If you follow the rule, basically a very modified chain rule, you can get the answer very, very quickly. The last thing I want to do once I erase all this, I want to give you one kind of almost like application problem. Okay, so for the application problem, let's say we had a function f of x equals to, let's just say it's 4 to the 5x. So a problem we've kind of been dealing with right now. And let's just say they give you the point 0, 1. And they said that you want to find the tangent line. So the tangent line equation. What would we do? Well, we'll do steps we would always be using to find the tangent line, but first let's just find the derivative. That's always the first thing to do. So we know the derivative, exponentials now, is going to be just the first part again. So 4 to the 5x, just rewriting it. Then it's going to be ln of the base, so ln of 4 in this case. And then we're going to multiply by just the top part here. So 5. Because of 5x, it just turns into 5. Okay, so now that we have that, how do we find the equation of the tangent line? Well, as you know, how we did it before is we first have to find the slope. And to find the slope, we just have to plug in the x value they give us in the point to the x, to whatever derivative is, and we'll get the answer. So in this case, we know that, essentially, we'll get, if we plug everything in, so this would be 4 multiplied by 5 times 0, because we know it's going to be 5 by 0, and then it's going to be to the ln of 4, there's no other x's, so just the ln of 4 by the 5. We're just going to be multiplying everything else out. Well, we know that this is going to be 0, and then for anything to the 0th power is 1. So we know that actually this whole thing is going to be 1. So we know that this is 1. Then everything else stays the same. And then if you're wondering, oh no, these things aren't going to really give you a number, that's okay. Your slope doesn't have to be a number. So it can essentially just be ln of 4 times 5, or to be a little more consistent in our writing, this would be 5 ln of 4. And this is a number, so I know it looks weird, but we can have that as a number. So the m in this case is 5 ln of 4. So now we just have to find the equation of the tangent line, and we have everything to do it. So we just have to remember that it's going to be essentially, or the equation for it is just going to be y minus y1 equals to the m minus x minus x1, and that's your equation. And we have everything for that. We have the 0, we have the 1, we have the slope. So let's just plug it in. So y minus our y1, so our y is 1, so let's just put a 1 here. And then our slope, we just calculated, is 5, the ln of 4. And then we have the x minus our x point, which in this case is just going to be 0. So 0. And we just have to simplify this. So y minus 1 equals to 5 ln of 4. And of course, x minus 0 is just x. And in this case, we just have to distribute the 5 ln of 4 to the x. So this is 5 minus 1 equals to the 5 ln of 4. Or we can write this in many different ways, but it's sometimes helpful because this is actually just a constant, the 5 here. We can squeeze the x right here, but you could leave it on the trailing if you really wanted to. You'd have to just ask your teacher. And then we just have to add a 1, just like normal in our equations. So that would be 5x ln of 4, so plus 1. So the 5x times the ln of 4 plus 1. And that would be your question, your answer to this question. So even if they give you kind of a weird function where you have to find the tangent line, the process is still the same when you first learn the process. So this is the derivatives of exponentials. I hope this helped. Thanks for watching.